Okay? In constant velocity, in a position versus time graph, or any position versus time graph, position is on the y-axis, time is on the x-axis. Okay? So x position, this one happens to be measured in centimeters. This means that our position is changing, right? As our position changes over time, that means we're in motion, right? And it looks like it's changing at a really constant interval because it's got a straight line, it's got a slope to it, it's not going any other directions, right? Our line is very straight and very simple. So that means every 0.1 second, we've moved 20 centimeters. After 0.2 seconds, we've moved 40 centimeters. After 0.3 seconds, we moved 60. 0.4, we moved 80. So that's a constant velocity, right? Does that make sense? We're not speeding up, not slowing down. So on a position versus time graph, the slope of a position versus time graph tells us the velocity of that object. Okay, so why don't you go ahead and put that down because we're going to need that. The slope of a position versus time graph always tells us the velocity of that object, okay, or of that whatever motion we're depicting. Okay. The slope of a position versus time graph always tells us the velocity. So how fast it's moving. Okay. Here we don't have any really indication in terms of direction, but what we do know is that we're moving in the positive direction, right? We're moving away from our starting point and we're moving in the positive direction. If our position versus time graph looks something like this, right, it went below the x-axis, that means after 0.1 second we would have been at negative 20, then negative 40. Okay, that means we're moving backwards 20 centimeters and 40 centimeters and 60 centimeters. Does that make sense? So on a position versus time graph, you have the ability to show moving forward and backward. Okay? What if on my first graph I had just gone, let's say here, and then I started going here, right? So I moved forward up until, about 40, and then I started moving backward. Okay, and if I stopped right here, what point have I reached again? The same spot I started, right? Even though time has passed, I went forward 40 centimeters, and then I went backward to my origin, to where I started from. Okay, so although time has moved on, this graph is just depicting the fact that we went forward, and then we came backward, and we ended up right where we started. Does that make sense? So on a position versus time graph, every time we cross the origin, that means we're back at where we started. Okay, and if our graph continued backward, that means that we'd move backward from where we started. Is that kind of making sense? Okay, you are going to have to be able to decipher graphs and tell me what's the motion that's happening based on this graph. Okay. Second type of graph is a velocity versus time graph. So believe it or not, these two graphs are telling us exactly the same thing. Okay, so on a velocity versus time graph, velocity is listed on the y-axis. Time is listed on the x-axis as usual. Okay, this is telling us that for every second that's passing, you don't really need to see the numbers for right now, but a straight line in a velocity versus time graph means we're moving at constant velocity. Right? We're not speeding up, we're not slowing down. Okay, and the slope of a velocity versus time graph tells us acceleration. And we're going to get into acceleration today. Yeah.
What are the units for velocity?
Usually meters per second. This one in particular is centimeters per second. So it's just whatever the graph gives you. Usually we're meters per second, though. Okay. So this is telling us that for every second that passes, or every tenth of a second that passes, we're moving 200 centimeters per second. If we were to do the math on this graph, we would find that the slope of that line is 200 centimeters per second. So these two graphs are telling us exactly the same thing. That for this 0.4 seconds of time, we're moving at a constant velocity of 200 centimeters per second, or 2 meters per second. Right? So if my graph, my velocity versus time graph look like this, what would that be? What would be happening? Yeah, we're decelerating or we're slowing down, right? In more common phrase, we're slowing down, right? We're going from 200 meters per second to 0 meters per second. But we're still moving forward. We still have a positive velocity. So this one does not mean necessarily that we're going back to our starting point, but it means that we're moving forward and we're slowing down. Okay, a velocity versus time graph is a little bit different. Okay, does that kind of make sense? Okay, if on a velocity versus time graph, I'm going to draw one more here so we can explore a little bit more. On a velocity versus time graph, right, this is velocity, this is time, this is my origin right here, so this is 0 meters per second. Okay, if I started here and then went here, right, there's my 0 where it crosses the intercept. I go from, let's say, 200 meters per second to what speed am I traveling at this point? 0 meters per second. As I go downward, I continue to go downward. What's happening to my speed? It's getting negative. Okay, but what's the negative tell us about a velocity? It's going backwards. So now we're speeding up in the negative direction. Right? Our velocity is going from 0 meters per second to 100 meters per second to negative 200 meters per second, right? Those two graphs tell us two completely different things. So you really have to pay attention to, is it a velocity versus time or a position versus time? And we're going to dive into graphs a lot more here in the next few days, but I want to introduce you to how you can view a graph to tell you what's happening.
So would that graph right there kind of look like if you threw a ball in the air?
Yeah. Very good.
Can the arrow go backwards on these?
No, because time always has to move on,
Okay.
right? Time has to move forward. So it's always going to be, we're always going to read the graph left to right. Yes, exactly. Right? So my velocity versus time graph could look like this, right? I'm going forward, I'm doing all kinds of crazy things, but it's got to be as time is moving on. So you're always going to read left to right. That was a good question. Okay, what if no, we just talked about that. Okay, all right, let's move on a little bit. So now that was constant velocity, right? We're moving at a constant speed. I showed you a couple at the end that were non-constant velocity, and we're going to look at a graph here that's non-constant velocity. You can sketch the graph roughly if you want, but we're just going to talk about what's happening in this motion. So if you want to take a few seconds and just roughly sketch, you can. If you want to just listen, that's fine too. All right, so first we're going to talk about basically what is happening in this motion, okay? Is it a velocity versus time graph or a position versus time graph? That's important to check first. Okay, it's a velocity versus time graph. Okay, it says that on the y-axis, velocity versus time. So we're looking at the increase or the decrease in speed or velocity as this moves along. Okay, so from point A to point B, what do we see happening? Just in plain terms, right? From A to B. We're speeding up, right? We're going from 0 meters per second to 20. We're speeding up. Okay, and are we moving in the positive direction or the negative direction? We're moving in the positive direction. So we're going forward and we're speeding up. Okay, and I'm okay with you using plain terms like that, right? We're going forward, speeding up. From B to C, what's happening? Are we stopped?
No.
No, we're at constant velocity. So we've got the cruise control set, right? We sped up, now we're on cruise control. What would have to happen on this graph for us to come to a stop?
We'd go back to 0.
We'd go back to 0, okay? On a position versus time graph, a straight line means we're not moving, right? But on a velocity versus time graph, a straight line means we're going constant speed. So straight line here means cruise control. From C to D, what do we see happening? We're speeding up in which direction? Positive direction. Okay, because we're still above the x-axis, right? Above the x-axis means we're moving in the positive direction. D to E, what do we see happening here? Staying constant velocity. So are we still moving forward?
Yep.
Yes, we're moving forward at 40 meters per second. Okay? So if I were to ask you, what's the velocity from, 5 to 8 seconds, you would tell me, oh, it's just 40 meters per second, right? You're just reading the graph. Does that make sense? Okay, from E to F, what do we see happening here?
Decreasing velocity.
We're slowing down. Are we moving in the positive direction or the negative direction?
Negative.
Positive. We're still moving in the positive direction. So we're going from positive 40 meters per second to positive 20 meters per second. So still moving forward. We're just hitting the brakes a little bit. Okay. Still moving forward, but we're slowing down a little bit. And then from F to G, we have the cruise control, right? We're staying still. And then from G to H, we're speeding up in the positive direction. So that whole time, this whole section, we were moving forward. There was at no point there that we were moving backwards. We would have had to cross the x-axis in order for us to start moving backwards. right? We moved forward that whole time, but sometimes we sped up, and sometimes we slowed down. Okay, are we on the same page there?
Yep.
Okay, so that whole graph we moved forward. Acceleration. Okay, the little line over here just means average. That's always what we're going to solve for. You don't have to include that. I only put that on there because your book does, but I will never write the line over it. Okay, A is just average acceleration. So change in velocity over change in time. Remind me what the triangle delta symbol means? Change in, right? Or final minus initial. Okay, always has to be final minus initial. A lot of times we like to just do bigger number minus smaller number. That's not always the case, right? If we're slowing down, our final velocity would be smaller than our initial velocity. Okay, so we just have to pay attention to that. So we talked about our velocity has the ability to be positive or negative. Okay, so a negative velocity means we're moving backwards, okay, or it's falling in the downward direction. Okay. Okay, a couple terms that we need to be familiar with is that anytime we're having a speed up, okay, whether it's in the positive direction or the negative direction, we consider that accelerating. Okay, so to be accelerating means you're speeding up. It can be in the positive direction or the negative direction. Okay, a lot of times there's a misconception that any negative velocity is a deceleration. That's not the case, right? Anytime we're speeding up, whether it's in the positive direction or the negative direction, that's called accelerating. Okay, anytime it slows down, something slows down, it's considered decelerating.
So if you're below like that.
So the thing about decelerating is that it doesn't necessarily mean your acceleration is negative. That's the tricky part. Just because we're slowing down does not mean that our acceleration is negative. Okay, so I'm going to show you an example of this just with some plain numbers. Okay, some plain numbers. So if we've got an acceleration, right, acceleration is always equal to change in velocity over change in time. So my acceleration, let's say our initial velocity was negative 30 meters per second, and my final velocity was negative 10 meters per second. Okay, would you agree here that we're slowing down? Right, we're decelerating. We're going from negative 30 to negative 10. So the negative here, don't think of that negative as part of the number, right? It's the direction. So we're going from negative 30 meters per second to negative 10. If I want to solve for the acceleration, it's always final minus initial. So final minus initial. Right, and let's say we did that in 10 seconds. Okay, when you subtract a negative, what happens to that? That becomes an addition problem, which means I'm ending up with a positive 20 over 10, which means my acceleration is positive 2 meters per second squared. Okay, sorry, that's the units for acceleration. We haven't really talked about that much yet. But the units for acceleration are meters per second squared. No, you don't have to put the plus. I'm just showing you that we started with negative velocities, yet our acceleration came out positive, right? And if you look at the slope of the graph, if you were to do a slope of this velocity versus time graph, right? Here's velocity versus time. We're going from negative 30 to negative 10. Right, the slope of that line is positive, right? So that's going to match the sign of your acceleration. Right, is that making sense? Okay, again, it's tough to try to memorize trends, but if you could just look at it with the numbers, you're going to see that trend come out. This one should be pretty easy. A sprinter increases from 5 meters per second to 7 meters per second over 1.25 seconds. What's their average acceleration during this period? Okay, again, average acceleration is what we're solving for all the time, so don't let that word throw you off. Velocity initial is 5. Velocity final is 7.5. And time is 1.25. Okay, so go ahead and grab your calculator. You might not need it for this one, but go ahead and grab it if you don't have it out yet. Is our acceleration positive or negative? positive, right? We're speeding up in the positive direction. So it's a positive acceleration. Very good, very good. Okay, her car accelerates at an average rate of 2.6 meters per second squared. Calculate how long it takes her car to go from 24.6 to 26.8. So this time we're given the acceleration. We're given our initial velocity and our final velocity. So when our variable is on the bottom of this triangle type equation, what are we doing? We're flipping these two spots. We're switching them spots. That's it. Okay, so that would leave us with t equals, let's see, 2.2 over 2.6. Is that right? Did I do that math right in my head? Hopefully. 0.8. 0.85? Okay. 0.85 seconds. We agree? Okay. Wrap up here. Velocity and acceleration are not the same thing. Okay, they don't have the same units. They don't tell us the same thing. So don't just think because they're part of a motion that they're the same. Okay? Velocity tells us the rate, okay, or how fast our position is changing. And acceleration tells us how fast our velocity is changing. Right? So that's the difference between these two. One of them tells us the rate at which our position changes. Acceleration tells us the rate at which our velocity is changing. So if you have an acceleration of 1 meters per second squared, that means for every second that passes, your velocity increases by 1 meters per second. For every second that passes, your velocity increases 1 meter per second. Okay, for every second that passes, you increase your velocity 1 meter per second. That's the way you can kind of talk through acceleration. For every second that goes by, my velocity is increasing by this much, or it's decreasing by this much. That's what acceleration is telling us. Okay, let's try this one. A car accelerates along a straight road from rest to 75 kilometers per hour in 5 seconds. What's the magnitude of the average acceleration? Okay, when I ask for magnitude, right, doesn't really mean anything. We're just looking for the acceleration. Okay, so what is it that jumps out to you here? From rest. Okay, that's good. And what's the other one? Kilometers per hour. Do kilometers per hour and seconds match? No. What would we like to have it in? Meters per second. Okay? So let's do that first. Let's do that conversion first. Is 75 kilometers per hour our initial velocity or our final velocity? It's our final velocity. So we need to go from 75 kilometers per hour to meters per second. Does anyone remember the shortcut? Times 0.2778. Okay? That's the shortcut, and I'll use it every time. If you don't want to use the shortcut, that's fine. The T-chart will work every time. Okay, but you multiply by 0.2778. We should get roughly a third of what our original was. So I don't know where we're at here. 21, 22, something? 20.84. Okay. So that means our final velocity is 20.84 meters per second. Okay, that's using the shortcut conversion. Our initial velocity was what? 0. Good, because it tells us from rest. That's important. Okay. And then our time is equal to 5 seconds. The reason we had to do that conversion is because if we set up our acceleration equation with kilometers per hour and seconds, our units for acceleration would not be meters per second squared, right? It would be kilometers per hour per second, and that's no good. That's not what we want. Okay. So acceleration is equal to final minus initial over time. 4.17 meters per second squared. Very good. Any questions? Solving for acceleration. Okay. Oh, we already talked about the conversion factor. Okay, cool. All right. With the person sitting next to you, I want to answer these two questions. Okay, so I'm going to give you two kind of hypotheticals or scenarios that I want you to try to come up with an answer for each. Okay. If the velocity of an object is 0, does that mean its acceleration is 0? And if the acceleration is 0, does it mean velocity is 0? So you're going to come up with an answer for those two questions. If you need to do a group of 3, you guys can do a group of 3. Okay.